Now
So,
we
hi
begin.
everyone. Welcome to our last lesson together on dark matter. And our topic for today is going to be direct detection of dark matter. Okay. So I'm not going to give an outline because, as you're going to see, this is going to be sort of encompassing everything that we're going to discuss together. And so this is really the last of those types of constraints or probes that we started sort of enumerating yesterday. And it's a very rapidly developing field of research. And so I really wanted to dedicate our whole lesson together today to this topic. And as you'll see, it's also one that I'm super excited about, very active in, and I think it's really a great this is a great time to be working on anything related to dark matter, but in particular, direct detection is really a field that's rapidly developing. So what do I mean by direct detection? The idea is that we could have, as we said, we have dark matter that's all around us. And we're going to be talking about how dark matter could potentially interact with some target that we put in a lab. Okay, so that's sort of the setup, that dark matter will interact with some target that sits in the lab. And this lab is typically underground. Okay. So the idea is, I'm going to have, here's my dark matter, it's coming in, and in some way it's interacting with my target. Okay, so here's my dark matter chi that's coming in. And often the way that we sort of think about how this interaction, might be happening is that dark matter, so this is also sort of a language that we'll be using. There's some mediator. I'm agnostic to what its nature is right now, but there's some way for dark matter to mediate interactions with the target, with the ordinary matter particles that are sitting in our lab. And so here's our target. And so this is sort of the way that I want you to think of this. Dark matter comes in and interacts with the target. And sort of a third way to really be thinking of this more generally is that, let me actually draw this down here, is that here's my dark matter. Okay, so another way to sort of think of this is that my dark matter is coming in, okay, and here's my target. And we're going to talk about all the different varieties of what this target could be. But something's going to happen. There's going to be some interaction, and we hope to measure that interaction. Okay, so this target, dark matter comes in, it interacts with this with the system that's sitting in our laboratory, and dark matter here is, let's say, coming out, and something's happening to this target. Maybe it's getting excited. Maybe it's shooting out electrons or photons or phonons or something. Okay, something is happening to this target, and what we're able to measure is what's happening in our laboratory. Okay. Now, I'll just sort of point out that, of course, in the context of the WIMP process, which was these 2-to-2 interactions of dark matter and standard model particles. So if we had dark matter that was annihilating into standard model particles like we'd have for the WIMP, then actually this same process kind of carries different, if we look at this diagram in different directions, and we get different ways in which we could have been probing the WIMP. And so, for instance, in this direction, this is indirect detection, which we mentioned yesterday, where we could see standard model final states that are coming from being initiated by dark matter interactions that are happening today. If we look at this direction, we're smashing standard model particles on each other and trying to produce dark matter particles. And that's, for instance, what we would do at colliders, such as the LHC. So this would be direct production. And finally, looking in the direction, in this direction, so sort of turning this around, this is the direction of direct detection, where what we're doing is looking at dark matter that's scattering off of some standard model particles that are sitting in our laboratory. So this is the direct detection direction. And in the context of the WIMP, which, as we said, has sort of been the prominent notion for many years, everything is sort of sitting together in this one, conceptually in this one diagram. But as we've seen, the theories and the mechanisms and the models of dark matter are so much more rich and diverse than just the case of the WIMP. And so more broadly, we're just sort of going to be thinking about these different directions of how we search and what kind of process we're going to be interested in a very different way. Okay, so and our focus today again is going to be on this direct detection diagram, which, as you see, is a cross-section that's not necessarily directly linked in the same way to the relic abundance as it would be for the case of the WIMP. Okay, so that's just a side note about sort of historically how people looked at the connection between these different ways to search for dark matter or to probe dark matter. But we're going to sort of release again. We're not going to be talking particularly about the WIMP. We're just going to be focusing on this particular direction of direct detection. So as you might know, we have actually many experiments that are searching for exactly this way via direct detection for dark matter. Okay, so we have many experiments that are searching in this way for dark matter. So just to start a laundry list, I'm not going to mention all of them, but just to sort of give you a sense of the types of experiments. So there's the Xenon 1-ton experiment. There's an experiment in China called Panda X. There's an experiment called CREST. There's an experiment called DarkSide. What else do we have? We have DAMIC, CDMS, Lux, and the list really goes on. Okay, so there are many types of collaborations, different experiments that are searching in this way for dark matter. And here's a typical plot that you might have seen, that these dark matter experiments typically show us as sort of, because we haven't yet found dark matter, what they do is place currently limits. And this is the type of plot that you typically will see. So here is, as a function of the dark matter mass, there's going to be some curves, some constraints that we can draw on. And these are typically on the cross section of the interaction between dark matter and the target sitting in the lab. And this is typically the dark matter nuclei cross section, let's say for spin independent interactions. But the idea is that typically you have, each experiment is placing its own curve of what I've excluded in this parameter space. Okay, and current limits typically go down to, let's say, 10 to the minus 46. Over here is sort of ballpark of GeV, 10 GeV and higher, okay? TeV and more. So what's happening over here? Just to sort of give you a sense, so this is a typical plot. Okay, not all these experiments are sitting exactly in the same place. They're all doing a slightly different coverage of this parameter space. But just to understand what's going on down here, so this type of behavior over here, of how this curve is behaving, this is a region where you don't care so much about the target properties or the thresholds. Really, just what's being determined is of the shape of this curve is just being determined by the fact that if we're talking about searching for dark matter, then we're proportional to the number density of dark matter. And so this goes like rho dark matter over the mass of dark matter. And so that 1 over mass is really what's determining the shape of this curve. And what's interesting and happening over here, this is a part, this region of where these curves typically lose their sensitivity. How exactly this happens and what's the shape of this cares a lot about both the target properties as well as the threshold of these experiments. Okay, so this is a typical plot that dark matter experiments might show. And the way that they reach these plots is that they have some detector of a certain size exposed for a certain amount of time. And one can go ahead in their detector and compute what is the expected event rate. How many dark matter, given the dark matter wind that is around us all the time, how many events would they expect to see in their detector? Okay, and so the computation for a rate has several different factors. Okay, so it cares about the target density. It cares about the dark matter flux that's hitting it. Okay. So we care about the target density, we care about the flux, we care about target properties, and of course we also care about the size of the interaction cross section between the dark matter and the target that's sitting in the lab. Okay. Now from all of these pieces, let me just start by mentioning this one over here. So this dark matter flux. Okay, this is what I was sort of insinuating before. So the dark matter flux is, what is flux? It's the number density of the dark matter times its velocity. So this is the number density of dark matter times velocity. And number density, as we just wrote above, is rho dark matter over m dark matter. And that's explaining this, this behavior over here of the curve. Now, the velocity of dark matter, so we talked about this a little bit. We do have a velocity dispersion. We said this is sort of ballpark of 10 to the minus 3 in natural units. But more generally, when you go ahead and compute the rate, what you do is really fold in the full velocity dispersion. So there's some integral d3v over some distribution function. So this is our velocity dispersion. And typically what people use, so for this velocity dispersion, this is typically what we call the standard halo model, which is a modified Maxwell-Boltzmann distribution. So it looks like F Maxwell-Boltzmann as a function of the velocity of chi. So there's some prefactor 4 pi, the velocity squared over some normalization function factor, e to the minus dark matter velocity squared over v naught squared times a theta function, which isn't letting us exceed escape velocity, so v escape minus v chi. And the parameters here, v naught is of order 220 kilometers per second, and the escape velocity of order 500 kilometers per second. Okay, and the density, of course, of dark matter in our local vicinity is 0.3 GeV per centimeter cubed. Okay, so these are sort of, this is sort of giving you a picture of how one computes this component of our dark matter flux. Okay. Now, what these experiments are typically doing, so let's actually take a look over here. Okay, so we understand now, we understand this, this behavior of the curve in this region over here. And as I said, if I look down, let's take a look at this region. Let's mark it like this region over here, okay? So this is something that's very common to all of the experimental curves. If you overlay each different experiment, is that all of these experiments are sort of shooting up when the mass of the dark matter drops to sort of the GeV-ish scale, okay? So what's happening in this region? Why do these experiments lose sensitivity? And the reason is that what these experiments are typically doing is looking for nuclear recoil signals, okay? So experiments typically look for nuclear recoils. Okay, so I might sometimes throughout this lesson today called nuclear recoils in short NR. It's not non-relativistic, which it was when we were talking about dark matter mechanisms, but now this is nuclear recoils. And so if you just think of this process that we drew before, okay, so here's my dark matter, let's say coming in, and it's depositing over here some deposited energy, which I'll call ED, and it has some momentum transfer for this process, which I'll call Q. And here we have dark matter that's scattered off of our target. Target is now going to be capital T. Okay, so the energy that's the energy of a nuclear recoil just goes like that momentum transfer squared over twice the target mass. Now you can work out the kinematics for a process like this. The momentum transfer roughly goes like the mass of the dark matter times the velocity. So I have that here squared over twice the target mass. And so if you plug in numbers, this scales like EV, where mass of dark matter here I've normalized to 100 MeV squared, and let's say a 20 GeV mass of a target, okay? And if we want to be able to detect that these nuclear recoils had happened, then of course this better be above our thresholds. So this has to be above, okay? We demand this to be above our thresholds, which are typically in these experiments of order a keV, okay? So, you know, let's say I had a dark matter particle that had 30 GeV mass. Okay, so let's say if m chi, just to sort of give you a ballpark, if m chi was 30 GeV, then you're going to get that the nuclear recoil energy is around 2 GeV, and this is great. Okay, this is fabulous. This is exactly what these devices were, what these experiments were designed to detect. But what you already see from here is that it's not so great when the mass of the dark matter is beneath a GeV. Okay, so not great for sub GeV masses. But you can actually understand everything that we just did just in terms of thinking of billiard balls. Okay, and that's what we're going to do now. Understand through billiard balls. Okay, so if I'm trying to detect a WIMP dark matter. Okay, that's like a big ball. So if I wanted to detect a WIMP, you can think of this as a large ball that's coming in. So here's my large ball, and it's coming in, and here's my large ball of a heavy nuclei sitting in the lab, and it makes perfect sense. Dark matter is going to scatter off, and my big ball is going to get a big kick, and I can detect it. So I can be a happy person, a happy experiment. Okay, but the situation is very different for light dark matter, right? So if dark matter is lighter, so what's going to happen? Then the kinematics is kind of like a tiny little ping pong ball that's trying to give a big kick to a big bowling ball. Okay, it's just not going to work. That tiny dark matter can't give a big enough punch to kick that heavy nuclei. Okay, so for lighter dark matter, which as we saw is something that kind of happens very generically for many mechanisms, the kinematics, let's just write out what we said, the kinematics is kind of like a ping pong ball trying to kick a heavy bowling ball. Okay, it just won't work. That light dark matter can't give a big punch. Okay, so that's going to look like, you know, here's my little dark matter trying to kick that big nuclei, and we're just not going to succeed. Okay, and this is why these experiments lose sensitivity when the mass of the dark matter is dropping beneath the GeV scale. Okay, that's when we sort of move into this light dark matter regime, and we can't give the big punch. And so if we want to be sensitive to light dark matter, which as we saw is something that we have generically in many dark matter mechanisms, then it's much smarter. Does anybody have an idea? How can I resolve this? If I'm keeping my dark matter as a tiny little ball, what can I perhaps do to improve my situation?
Just light targets.
Exactly, to scatter off of, to interact with something that's lighter, where the kinematics is more well matched. And does anybody have an idea of a very particle that we have in many systems that's very small, smaller than a proton?
Electrons?
Electrons, exactly. Okay, so it's much smarter to scatter off of something lighter. And in particular, we can use electrons. Okay, so that's exactly the idea. Here's my little dark matter, little electron, and everything works perfectly, and everybody can be happy again. Okay, and this basic understanding that you guys have just been able to understand from this, from phrasing it in this way, this really is the basic understanding, the basic concept that sits at the base, at the core of many of the new ideas that have been proposed in the literature over the last decade. Okay, so this is the basic idea that sits behind many of the novel ideas in the literature. Okay, so to understand the particulars of these ideas, I'm going to provide you now with the following energy guideline. Okay, so let's look at the following energy guideline. Okay, so if we're talking about dark matter scattering events, then, okay, so if I'm talking about scattering events, then the maximum energy that my dark matter particle can possibly deposit into the system is all of its kinetic energy, right? That's all that it has to give in a scattering event. So the maximal deposited energy is the entire kinetic energy that the dark matter particle is carrying, okay? And so this kinetic energy, of course, roughly goes like mass squared over v squared times v squared, sorry, mass times velocity squared. I'm dropping, of course, factors of half. Velocity, I remind you of order, ballpark, 10 to the minus 3. So this means that I get here 10 to the minus 6 times the mass, okay? And so what does this tell me if I look, say, at, here's my scale of dark matter masses, okay? And here's going to be the scale of what type of energy deposit do I need to be sensitive to. Let's write this clearly, energy deposit. Okay, so this tells me that if I want to be sensitive to GeV dark matter masses, then I need systems that can be sensitive to 6 orders of magnitude less in energy. And so I get over here the keV scale. And this is exactly what those WIMP experiments were designed to do, what these nuclear recoil experiments are designed to do, okay? But if we want to be greedy and we want to go down 3 orders of magnitude to the MeV scale, then we need systems that are sensitive to much smaller energy deposits, right? Now we need systems that are sensitive to really small energy deposits of electron volts. And if I want to be really greedy and go another 3 orders of magnitude down, all the way down to that warm dark matter limit of a keV, then I need systems that are sensitive to really, really small energy deposits of order milli electron volts. And so you can actually organize kind of all of the ideas that people have been proposing in recent times, new directions for searching for dark matter based on sort of the size of that energy deposit that the systems are sensitive to. Okay, so all I have to do now is kind of focus on, okay, this energy deposit. So let me just draw this down here in a clear way. And I'm just gonna, obviously I'm not gonna be able to cover all of these, but we can all organize all the ideas based on the size of this energy deposit that they're in principle sensitive to. And I'm going to draw this in the following way. Oops, sorry. So let's do like this. Here's my energy deposit, and here I have keV, EV, and milli EV. So okay, here's sort of a long list. So we have atomic ionization ideas. We can use semiconductors. And in this context, people have thought about, so for example, silicon or germanium or diamond, we've actually recently shown is great for this, and silicon carbide, as well as others. You can use scintillators, such as gallium arsenide. You can use graphene, okay, and many others. If we want to go past that EV, past the EV region down to the milli EV region, then some ideas that exist are to use superconductors. So for this, just as an example, you can think of using aluminum or niobium nitride or tungsten silicide. You can use topological materials called Dirac materials. You can use heavy fermion systems, as well as others. And these ones that I've written up here, I'll take advantage. So all of these ones that I've written above kind of use interactions, just like we discussed, with the electrons in the system. And there are actually also some nice ideas about how you could use interactions with nuclei, but in a smart way, where you're really looking at interactions with phonons. And so just to list them over here, so in this region, we could think about using color centils, like crystal defects in crystals. And down here, we could be using superfluid helium, as well as polar crystals. Okay, so these few ideas that I've written down here are actually using interactions with nuclei via phonons. Okay. Now, obviously, I haven't written every single idea that exists in the literature. I've tried to sort of give you broad categories, and obviously we're not going to be able to explain all of these different systems. So what I'd like to do in our time together today is kind of walk you through a few of these ideas to give you sort of a combination of a sense of what kind of materials people have thought about, what kind of methods, what kind of processes, detection philosophies, to sort of open your mind in this direction. Okay. So that's what we're going to do together. I'm going to walk through a few of these to get a taste of materials, different methods, different processes, and different detection philosophies. Okay. So before we start our first example, just a couple of side notes, but they're important. Okay. So let's go here. Side note. Okay. So first side note. So if you remember, we wrote down our rate very early on, and there were a bunch of different factors, and we explained the dark matter flux. But if you remember in that rate, we also had a cross section, right? So that's, sorry for scrolling. Where's the rate? Okay, here we go. Remember this cross section that's out over here. Okay, this was parameterizing the interaction strength, the cross section of our dark matter with the target sitting in the lab. And so I just looking at that cross section. So let's write like this. In our rate, we had this interaction cross section, and I just want to point out the way that you'll see it typically appearing in the literature. So typically what we do is we write it as some reference cross section times a form factor. Okay, so it's typically written as a reference cross section times a form factor. Okay, so what I mean by that is you'll often see something like this. So let's say so sigma E, because I'm talking about interactions of dark matter with electrons. And the fact that it has a bar sitting on top is the fact that it's a reference cross section. Okay, so this reference cross section, what we mean by this is that it's a cross section at some fixed reference momenta. Fixed reference momenta transfer, which is typically taken to be of order alpha ME. Okay, and the reason this is chosen is because this is sort of the typical momentum transfer you expect in semiconductors, which were the first ideas that people sort of put forward in this context. So this is the typical value for semiconductors. Okay. Now, why is that important? What do I mean by that there's a reference momentum? If you remember in this diagram that we drew here, where is it? Over here, right? There's the cross section cares about the energy deposit and the momentum transfer. But what we do in order to be able to set limits in sort of a consistent way, or sort of in comparing apples to apples, is really just to be able to plot independent. So we're going to plot things as a function of sigma bar, which has a fixed reference momenta, and then we accommodate. We sort of make up for the fact that we've taken out that reference momentum, where we include now a form factor. Okay, so that's the next piece over here. Is that the second piece over here is that we now have this times a form factor, which is typically a capital F dm. So this is a form factor squared. Okay, so this is our correction for the momentum dependence. This piece over here corrects for momentum dependence. Okay, so we have, so if we have here is our dark matter, where we have this energy deposit and momentum transfer scattering off of electrons, then, if you think of this diagram, if I'd really be computing this diagram, then what I'd get is a propagator, right? So I'd have a propagator, and the propagator is going to look like 1 over, the mass squared of whatever particle is mediating plus my momentum transfer squared. And we are in a regime, when you do the scattering, if you work at the kinematics, you'll see that the energy deposit is much smaller than the size of the momentum transfer, which is why I've written it in this way. But basically, what this means is that if I'm sort of taking this reference cross-section times times a form factor, is that I have a form factor as a function of Q, which is in the very heavy mediator limit. Okay, so when let me write this down here actually, so we have more room. So if this is my propagator, then what is my form factor as a function of Q? So if I look at the limit where the mass of the mediator is much larger than that reference momenta, okay, then alpha ME, then this term over here is going to dominate. Okay, and that means that my cross section had no momentum dependence, and that's why I don't have to correct for it. So basically this form factor just looks like 1, whereas in the opposite regime, where M phi is very light, is smaller than alpha ME, then we have to correct for the fact that we've put in this reference momenta rather than the real momenta in the following way. Okay, so this first regime is what we call the heavy mediator case, and the second is the light mediator, sometimes referred to as massless, but it's enough that it's lighter than the reference momentum. Okay, and so I'm mentioning this because what's going to happen if you look through the literature, or if you delve into this topic yourself with some new idea, you'll often see results or projected reach divided into these two cases: what happens for the heavy mediator case and what happens for the light mediator case. Okay, and the difference is you're always going to show your reference cross section. The question is, what was your form factor that you used in this computation? Okay, so this is what you often see. Results or projected reach for each of the heavy or the light, or heavy or light mediator separately. Okay. Okay. Now, the second side note that I wanted to make is that, again, if we scroll back to that, to where we wrote down the rate, then we also wrote down that the rate was proportional to target properties. Okay, so rate was proportional to target properties. Okay, and so kind of historically, the way that that these target properties were computed in the literature is by looking at the overlap of what's my initial state wave functions, what's my final state wave functions, and in particular, the language that was always used there was for single particle excitations. Okay, so historically, this is computed, or was computed, by the overlap of single particle excitation wave function. Okay, so if I was teaching this this course maybe even 5 years ago, and actually probably even just 2 years ago, it would be taught somewhat differently, because what one would do is, in your given target, you have to figure out work out the single particle excitation wave functions and do the overlap, and sometimes it gets very messy because these systems are, the electrons aren't free particles, and so everything about the system has some complications. But what we now actually know through recent developments just over the last year is that we actually have now a much more general way to not work in the single particle excitation picture, but really a more general and accurate way that automatically accounts for all of the collective, all of the many body effects, let's call it, all of the many body effects that these systems have. Okay, so we now have a more accurate and general way to do this computation that automatically accounts for all the many body effects of the material. Okay, and the idea is over here that we use, this is because the properties of the material, how it responds to some weak probe that's coming in, that's a property of the material that's completely determined by the dielectric function of the material. Okay, so what we use is the dielectric function of the material, or alternatively, what we construct from it, which is called the loss function of the material. Okay, so the loss function is defined to be the imaginary part of minus 1 over epsilon, where epsilon is the dielectric function, which is a function of Q and omega. Okay, so both the momentum and of energy. And what I mean by this, just to sort of draw pictures, here's my material. Okay, and I have some weak probe that's coming in here. So here's my dark matter that's coming and interacting with this material. The material has some response. Okay, and that is literally the definition of the loss function of the material. Okay, and so we don't actually have to break it down into sort of individual single particle excitations, but there's actually a complete response of the system which automatically accounts for all of the many body effects, and importantly also for collective behavior in the material. Okay, and so the response, because this dielectric function or this loss function is exactly the response of the material, or response of, let's call it, of the system to a weak probe. Okay, and what's really beautiful here is not only do we have good analytic functions that describe this, but really this is something that you can go ahead and measure. Okay, so people measure the loss function of materials, and you can just go ahead and take this data, take these measurements, which is a complete picture of what your material, how your material responds, and understand from that how you extract the dark matter interaction rate. Okay, so this is a really very powerful new tool, and so you can read about this in the paper, the PRL that we put out last year. So this is 2101.08263. Okay. And again, I just want to stress this, that the fact that we can both measure this and that it includes not just the single particle excitations, this means that in particular it also includes things like plasmons or any other collective modes. And when you go and look through data or sort of try to understand what are properties of materials that you'd want for optimal materials, this really allows you to identify optimal materials for dark matter detection. So this allows us to find optimal materials through looking at sort of energy matching of what are the properties of the material versus what are the properties that I would want in order to maximize the impact of the dark matter interactions. Another nice thing about this, which I'll just mention, is that when you have something that's like a physical, it's a physical quantity, it's not some broken down components of it. There are a lot of ways you can also catch mistakes that exist in the literature. So for instance, there are some rules that this loss function has to obey from charge conservation and from causality, and that actually allows to also to really understand what's right and what's wrong within the analysis that existed in the literature. So this is really a new powerful tool that one can do for any material. Okay, and so for that reason, we're not actually going to be going into breaking down and writing down all of the wave functions per material. Any material you want, go ahead and write down the dielectric function or take data, and you're going to have the results. Okay, so that concludes my my side notes. Before we go ahead, and this is what we're going to do after the break together. We're going to go ahead and, as we said, sort of look at this. We're not going to go through the entire laundry list of ideas, but we're going to walk together through a few of these different ideas to give you a sense of materials, strengths, weaknesses, different detection methods, processes, and philosophies. So that's where we're going to come back after the break. Are there any questions so far?
I have a question. Mm-hmm. For this loss function, I don't really see, why is it different to looking at the phonons or anything like that that are moving through the material?
It's not an issue of if it's different from phonon. So I can give you an example. Okay, so let's say a free electron gas, which is just, so I can write down a dielectric function for that. I can also write down initial state wave function, final state wave function, and compute the overlap. When I do that, I'm going to be missing a collective excitation, which is the plasmon. And the plasmon has some characteristic energy, which is different in different materials. But just the fact that that plasmon has some width, even the tail of that distribution dramatically changes what is the response of the material. Okay, and so neglecting to include that effect is something that's very problematic and would lead you to think of a wrong type of suppression that happens in your rate. Now, basically, all I'm saying over here is that another thing that we're able to identify in this way is that this is actually something that also was mentioned yesterday in the discussion session. If I think about something interacting, so it's been well known for a long time that if I have a photon, when it travels through material, it picks up a mass. What does it mean it picks up a mass? It's exactly this. I have some I have some in medium effect. Okay, and for a while it was thought that the only type of particle, the only type of, let's say, dark particle which would experience in medium effect would be a dark photon, because I think of a dark photon that kinetically mixes into a photon, and the photon has in medium effect. But this more general analysis enables us now to understand that actually in medium effects are identical as long as the interaction that I'm talking about is an interaction that only cares about my electron density. Okay, so as long as it's any spin-independent interaction, whether it's a scalar mediator or a vector mediator, when I'm talking about the scattering, the in-medium effects are identical. Okay, so this is what when we start looking at something from, you know, if you look at like the proof of this, which is the proof is just beautiful, because it's like you sit down, once I tell you the answer, you can go ahead and prove it yourself. This is just a linear response. The only thing that these measurements care about, or that this dielectric function cares about, is that I have a weak probe, and that, you know, everything that's happening in the strongly correlated system is being unchanged by the fact that as I'm probing the system, but everything about the response of the system is the same, and then it doesn't care if it's a photon or anything else. So this is really a much more powerful tool. It also, by the way, takes, you know, when I used to compute these superconductor constraints, my computer could run for a very, 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 very long time to get me one curve. And now it's like, it's instantaneous, because the function that effectively describes everything way more accurately, including all of the collective modes, it's such a simple function that you can just write down, and within a second you have curves that used to take me days to run on my laptop. So there's also that gain, but I think really the main one is just this sort of big picture where you realize this is actually the full result, and it includes everything, and I can match it onto data, and it holds way more broadly.
Okay, thanks.
Sure. Any other questions?
Okay, so when do we want to start again? There is a raised hand, so I don't know, Yonit, would you like to take the question
we can
first?
start. Yeah, sure. Okay. Leonardo.
Hi. So I have a question on the very last thing you said. So is that statement true for all types of dark matter electron interactions, or are there some caveats?
The use about the dielectric function?
Precisely, yes.
Yeah. So I'll be cautious. The one that I can say for certainty, because as you see, this is a very fresh direction. This is true for spin independent. So the analysis should hold for any case where my interactions are basically just interactions with the electron number density. So if I think of my Hamiltonian, that means that all I have is like just the positions of the electrons. And so this should hold for any spin-independent interaction, so a scalar mediator or a vector mediator. Okay, so not for spin-dependent, not for, you know, I could think of more, less of different types of interactions. For the most part, though, when people, also for direct detection experiments, when they, usually when you see like the money plots for a new material or for existing experiments, for the most part, people look at spin-independent interactions, or also sometimes spin-dependent. And for those, it might be we haven't yet worked out. Certainly, the proof that I've done in this paper doesn't hold as is in that case. But this does tell you that that an interaction that's interacting via a vector or a scalar are screened identically in the scattering case.
Okay, thank you.
Sure. Okay, so welcome back, everyone. Anyone who's willing and able to put on video, please, please, pretty please. I'd super appreciate it. Okay, so having mentioned these two side notes about pieces related to the rate and how results are presented, and what methods I think are very easy, promising, and the most accurate for computing these rates, we're now going to delve into a few examples together. So I'm going to start with my first example. Example number one, and these are actually the set of the first ideas that were proposed in the literature roughly a decade ago. First ideas. And so here are the ideas that maybe we can use atomic ionization. Wow, awful writing. More awful than usual, I apologize. Atomic ionization. Or maybe we can use semiconductors. Let's understand how this works. Okay, so maybe in the context of atomic ionization, here's my atom, okay, and here's my little electron. Okay, obviously this is not what a real atom looks like, but for our cartoon picture, this will suffice. And here's my dark matter that's going to come in, and maybe it's going to interact with that electron and deposit enough energy to ionize the atom. Okay, so this would be this is one of the first ideas that was put forward, and you can read more about this in Essig et al. In 2012. Or maybe dark matter is going to come in and interact with electrons in a semiconductor. So this is roughly sort of the band structure in a semiconductor as a function of momentum. Here's energy, and I have my valence band and my conduction band. Here's my valence band and my conduction band. And maybe dark matter is going to come in and deposit enough energy to excite an electron up from the valence band to the conduction band. Okay? And so, and let me actually just give you a reference over here. So if you want a lot of details but in the computation using single particle excitation, because it's an older paper, there's a lot of information about this in 1509.01598 for more details. But the basic idea is already in this paper from 2012. Okay, so in these systems, let's just work out what the energies are. So for instance, if I'm trying to ionize an atom, so let's say in a typical atom like xenon, this is of order 10 eV. Okay, so this is, for instance, for xenon. And in a typical semiconductor, whether it's silicon, germanium, as a diamond, silicon carbide, sort of a standard semiconductor, the energy gap, okay, this gap between the minimal energy you need in order to be promoted from the valence band to the conduction band is of order in eV. Okay. Sorry. And so based on that energy guideline that we discussed together, this should tell us that in these systems, we can hope to detect dark matter masses, which are 6 orders of magnitude above, right? So of order MeV and above. And these ideas, which were originally proposed by theorists, are being experimentally realized these days. And I'll just mention 2 of sort of the big experiments that are sort of leading the charge. So one is called Sensei, and the other is called Super CDMS. And I'm not going to go into both of them. I'm just going to sort of, let's talk for a moment about what Super CDMS does. Okay. So what Super CDMS does is they use a philosophy for their detection that it's called excitation concentration philosophy. So let me explain what this means. This is excitation concentration philosophy. Okay. So the idea is that they have some big bulk of their semiconductor, and dark matter comes in and it's going to interact with the electrons in the semiconductor, deposit enough energy to excite the electrons, and then they kind of let these excitations sort of ricochet around until they can collect and detect them. Okay, so the idea here is that they let the excitations ricochet around, sort of random walk around until they can collect and detect them. Okay, so here's sort of the picture to keep in mind, obviously not drawn to scale, but here's my, let's do it this way. So here's some, here's my semiconductor bulk. So it's some silicon, let's say, and for both Sensei and Super CDMS, the semiconductor that's sort of, most well-known, well-studied, most developed for other purposes is silicon. And so right now they've been working with silicon. So imagine I have some, some puck of silicon. Okay, so this is my big target that dark matter is going to come and interact with. And then instrumented on the surface, I have some collection fins where I hope these excitations eventually get collected to. And on top is sort of a tiny little detector, which in their case is a transition edge sensor, or in short, a TES. Okay, so let me just write out what this technology is. The technology that they're using for their detection is a TES, which is a short for transition edge sensor. So what this TES is actually, it's just a tiny little superconductor. You can kind of think of it as a very sensitive heat calorimeter or a heat bolometer. Okay, so this is a superconductor. It's a superconductor, and it's really just a sensitive bolometer. So the idea is that that you take this superconductor and it's sitting in a self-biased system, a self-biased circuit, so it's exactly on sitting like on the threshold between the normal to superconducting state. Okay, so here's what's the resistivity as a function of the temperature, and so there's some it's basically sitting right over here on this threshold between am I in a normal state or in a superconducting state. And so very small energy deposits can lead to very, very large changes in the resistivity, which leads to a very large change in the current, which they can then read out. Okay, so it's that's sort of the idea behind this this type of technology. And so a decade, let's say decade-ish after this idea to use semiconductors was initially proposed, we now really have experiments which are exactly going after this. Okay, so a decade after the theory proposal, we now have these realizations in experiment. Okay, so this is the semiconductor idea, and leading the charge for the electron ionization, for the atomic ionization idea is experiments like that are using xenon. So obviously we have many experiments that are using xenon because that's what often is used in the context of the nuclear recoils. And so experiments like xenon 1 ton, etc., are leading the charge with the electron results in the atomic ionization realm as well. So we have some great experiments that are searching via semiconductors, also atomic ionization, for dark matter. But as we said, we can't go in these systems below the MeV scale. That's just something that inherently we can't do through electronic excitations because of the gaps of these systems. So what happens if we want to go lower? Okay. What about masses that are beneath the MeV scale? So for that, in comes example number 2. Okay. So my second example are going to be superconductors. Okay. So what happens in a superconductor is that the ground state of the superconductor, it's no longer, the electrons are no longer free electrons, but it's energetically favorable for them to follow the buddy system. Okay, so they pair up in pairs that are called the Cooper pairs. So ground state of superconductors are called Cooper pairs. And the binding energy of these pairs, which is the same as the gap of the system, is of order milli-electron volts. Okay, so the binding energy, which is the same as to say the gap of the system, is of order milli-eV. And so based on that energy guideline that we worked out together, this would tell us that we could be sensitive to dark matter masses that are now, again, 6 orders of magnitude above, so down at the keV scale. Okay, so some 3 orders of magnitude lower than the semiconductors and the atomic ionization. So the idea here would be that dark matter is going to come in, it's going to scatter with these Cooper pairs, okay, it's going to deposit enough energy to break the Cooper pairs apart, and that's going to create excitations that we can somehow collect and detect. Okay, so the idea is that dark matter comes in, scatters with these Cooper pairs, that's going to deposit enough energy to break them apart, and then that creates excitations that we can collect and detect. Okay, and you can think of doing this using this idea in many different ways. So actually, in the first idea that we put forward in this context, maybe around 6 or 7 years ago, was to use kind of an idea very similar to what we did here for supersede MS. Okay, so kind of inspired by that. Imagine if instead of the silicon puck, I now just sort of opt out the silicon puck, and instead I'll put a puck, like a bulk of a superconductor. Okay, so now instead of having silicon with just my little sensor being a superconductor, I'm now going to have a big superconductor bulk, and then I have this excitation concentration idea happening within the superconductor. So that was sort of so one option which was our first idea, would be to use bulk, and this is a bulk superconductor, which is very similar in spirit to what we just discussed about what super CDMS is doing with their silicon, and this you can read about this in 1504.07237. But what I want to instead of repeating that same detection philosophy, what I want us to understand now together is actually a different detection philosophy, which we put out more recently, which I'm going to call the target plus sensor philosophy. Okay, and you can read about this in this PRL that we put out, 1903.05101, and actually some new results are out. I'll give you, we just put this out 2 months ago, 2110.01586. Okay, so here's the idea. And I'll tell you the idea in the context of the particular technology that we've used, but it's actually much more broad than that. So for this, imagine that I use the following technology. I'm going to call it, has a long, annoying acronym, SNSPD. Okay, so this is superconducting nanowire, superconducting nanowire, single photon detector. Okay, so these SNSPDs in short, which are just tiny little nanowires that are superconductors, is a very mature technology that was originally developed for a completely different field of research, touching upon one of the questions that we had yesterday in the discussion session, something that people have been working on for a long time with incredible results for quantum information science. Okay, so this is a mature technology developed for quantum information science. Okay, so the idea is that we're going to use, so we have this little nanowire, okay, and it's in a superconducting state. It's a superconductor, and it's again sitting in some self-biased circuit, such that that what's going to happen is that dark matter is going to come in, deposit enough energy, and that's going to sort of create a hot spot across this nanowire. And then the electrons diffuse away, and that creates a voltage pulse, which we can then read out. Okay, so here's let me just write that out. So we have a nanowire is in a superconducting. So superconducting, I might sometimes write shorthanded as SC, superconducting. It's in a superconducting state, and it's sitting close to the critical value, close to some critical current, and then we're going to have some energy deposit by dark matter that's going to create a hotspot, and then our electrons are going to diffuse away, and then we're going to have some resistive region now across this wire. So resistive region across the wire, across the nanowire, and that's going to result in a voltage pulse. Okay, so just sort of to give you like the image, so obviously not drawn. My experimental collaborators would hate this picture that I just drew, but that's sort of what you can think of. This is what the nanowire looks like. Okay, it's very, very, very thin. The one that we were looking at size-wise was around 400 microns squared. Okay, and this is considered large for nanowire purposes, but obviously very, very, very tiny. And so the idea is that we basically propose, let's take this very mature technology and apply it for the first time towards the dark matter hunt. Okay, so that's what we proposed, is to apply this technology for dark matter. And the idea is that we use this nanowire simultaneously as the target with which dark matter is going to interact, as well as the sensitive sensor that's sensing that this interaction occurred. Okay, so that's the idea of this philosophy, that we use this same nanowire as both the target as well as the sensor. Okay, and this technology already has very low energy thresholds that have been demonstrated. So the lowest energy threshold for nanowires that currently has been demonstrated is at around 125 milli-EVs. Okay, so very, very low already. And in fact, we're nowhere near the fundamental limits for this technology. So in principle, we should be able to push down even further in thresholds, but this is already an extremely impressive low energy threshold. And so just to give you a sense of how, if you have a good idea for some material that can really probe something, some new region of parameter space. So as I mentioned yesterday, in these two papers, so we have a tiny little nanowire, and I say tiny because it's really tiny. Okay, it's we have a prototype nanowire that is 4.3 nanograms of material. Okay, it's super tiny. At the time of the first paper, we had looked at it for 3 hours and seen no events, no dark counts. By now, we actually have 180 hours of data. And just using this 3 hours of exposure of a 4 nanogram device, we were able to set the strongest limits on dark matter parameter space. Okay, the threshold of this device that we used was just of order 0.8 eV. In our newest paper, we've discovered that our nanowire is actually a little lower at around 0.7. Okay, so just thanks to this very low energy threshold and the promise, the material properties of these targets, we can really probe deep into uncharted regions of parameter space. And this idea in principle should allow us to go all the way down to sort of that keV scale, probing milli-eV energy deposits. Okay, so far we've done, we have 2 examples that we've worked through. We've talked about using semiconductors and atomic ionization. We've talked about a way in which we could go even 3 orders of magnitude lower in mass, down to the warm dark matter limit of a keV. But the third example that I want us to discuss now is related to the question of, can we extract directional information? Okay, so this is going to be our third example, which is directional information. Okay, so if you kind of think for instance about this, this picture that I drew here for super CDMS, or what I mentioned we could do with bulk superconductors. If what I'm doing is I have some dark matter interacting with my material, and then I have these excitations and I let them kind of ricochet around and random walk around until I can collect them, then I'm losing, once I let them ricochet around, I'm potentially losing the directional information of where did that initial excitation come from. Okay, so by looking at these sort of secondary particles, we potentially lose information about directionality. And directional detection of dark matter has long been recognized as a very powerful tool when we want to search for dark matter, because directional information gives us a way to really distinguish signal from backgrounds, and it gives us a daily modulation rate. Okay, so let me just write that out. Sorry here for scrolling. So this has long been recognized as a powerful tool of daily modulation. Long been recognized as a powerful tool for direct detection, because it gives us the ability to separates signal from background. Okay, so sort of heuristically, here's my, let's say here's my dark matter wind. Okay, here's my dark matter wind coming in, and here is us on planet Earth. Okay, and here's some relative axis. And imagine at some point during the day, here's my experiment. Okay, but now as Earth is rotating around its axis, 12 hours later, my experiment is now sitting over here with this direction. Okay, and so in principle, by being able to distinguish where's the direction that my event is coming from, we can hope to actually be able to say, if we were to see something, this is really a signal because my background shouldn't be behaving this way. Okay, so that's the basic idea. And at least in these sort of original ideas to sort of use this excitation concentration philosophy, it's potentially difficult to achieve this directionality. I say that with caution because we recently actually have an idea of how to do this potentially in superconductors. But let me walk you guys through a very easy way in which this could happen, which is that if instead of looking at these secondary excitations, which I let ricochet around, I'm instead detecting the primary electron with which we interacted. Okay, so that's going to be the idea that we're going to do. Instead, we're going to look at the primary electron, and this is something that we can hope to do with 2-dimensional targets. And in particular, I'm going to tell you the story now for graphene, but keep in mind that you could actually do something very similar even using these nanowires, okay, which are also two-dimensional. Okay, so what is the idea over here? So what I mean is here's my graphene, and I'm going to look at sort of the primary ejected electron from this two-dimensional surface. Okay, so yeah, let me just write this down. Sorry. Yeah, so this is we're going to look at the primary interaction. That's sort of what's going to sit here at the core. So graphene, I know we're not condensed matter physicists, but graphene, it's a two-dimensional material. It has a vanishing or nearly vanishing band gap, but you actually don't need to know any of the beautiful properties of graphene, okay? All we have to know is that in graphene, and actually in many materials, if I want to eject an electron from the material, then I have to overcome two things. One is whatever is the gap in the system, which in this case is tiny or non-existing. The second thing is what's called the work function, which is literally defined as how much energy do I need to deposit in order to eject something from the material, okay? And the so if I have this, I have here this surface. Sorry, let me change colors here. So I have this surface, and I want to ask, what energy do I need in order to eject an electron? Well, that's of order the work function, which is of order a few eV. Okay. And as a side note, this is not true just for graphene. This is actually for most materials, or for many materials. And so based on that energy guideline that we worked out, who wants to tell me what dark matter masses I can hope to probe with this method? If I need eV energies to eject a material, to eject an electron, then I need 6 orders of magnitude larger in mass. So this is going to give me the MeV scale. Okay. But the real strength of this proposal doesn't come from the fact, it's probing the same mass range that like the semiconductors are. But the real strength comes from the fact that it turns out that if you track that direction of the ejected electron, okay, the ejected electron tracks the direction of the incoming dark matter particle. Okay, so that's really the important part over here. That the electron, the ejected electron tracks the direction of the incoming dark matter particle with which it interacted. Okay, and what this means is that this is now going to give us this gives us directionality. And in the simplest form of directionality, what it gives us is what we call a forward-backward discrimination power. Okay, so this gives us directionality, or a forward-backward discrimination power. Okay, so what I mean by that is, imagine at a certain time during the day, here's my graphene sheet, okay, and here's my dark matter wind coming, let's say, from below. So my electron, which is ejected, is going to go in the forward direction, and I'm going to detect it. Okay, so here's my ejected electron. But now let's fast forward to, so we were in this situation right now, and now I'm going to fast forward to 12 hours later as Earth has rotated around its axis. Now the relative orientation is, here's my graphene plane, dark matter wind coming in from on top, and that electron is ejected towards the bottom. Okay, so into the substrate where it's detected as something different. Okay, so fast forward to 12 hours later, here's still my graphene sheet. Now dark matter wind is coming in from on top, and my electron is going ejected into this direction. Okay, so this naturally gives us a way to construct a forward-backward asymmetry, or gives us sort of this head-tail or forward-backward discrimination power. And this idea has actually been officially adopted by an experiment that was not planning to search for dark matter at all. So there's an experiment that's planned to be sitting in Gran Sasso in Italy, which is called the Ptolemy Experiment. Which is originally proposed to search for relic neutrinos through their capture on tritium, except it turned out that their tritium was going to be sitting on 0.5 kilogram of graphene. So we essentially just proposed to them, well, why don't you use your bare graphene sheets before you load it with tritium and run it as a directional detector of dark matter. Okay, so this idea has been officially adopted by them, and you can look at our paper where we first proposed this idea for graphene. It's 1606.08849. Okay, so this is the original paper, and now part of the Ptolemy program. Okay, so we've gone through a few examples and a few different sort of, not just materials, but different processes and detection philosophies. And, you know, anytime somebody gives you some new material, as we said, we have to go ahead and compute what is the rate. So let me just sort of give you a picture of where all of these things sit in terms of dark matter parameter space. So let's just draw this over here. I don't want to, okay, I'm going to draw it down here so that it doesn't get chopped when I send you the PDF. So let's look now at what we expect. Here's my dark matter mass, okay? And now on my y-axis, instead of writing that cross-section with nuclei, which is what experiments until now had typically done, let's look at our cross-section with electrons. And as I said, what you're always going to see in the literature is sigma bar. So this is the reference cross-section. And I have to tell you if it's a light mediator or a heavy mediator, the stuff I'm going to draw right over here right now is, for instance, for a light mediator. Okay, but you'll see the equivalent in the literature as well. Okay, so what happens is that we have, as I said, we have a lot of different proposals. So it's actually, okay, we have some existing constraints, as I said, from, you know, combination of all the xenon-related materials and all the xenon-related experiments, as well as super CDMS and Sensei, etc. And so we have some constraints that are sitting sort of, oh, let me actually give you, sorry, access over here. So actually, let's start this at GeV. So everything I'm drawing is beneath that, you know, is in the sub-GeV in the light dark matter regime. Here we have MeV, and here going all the way down to sort of the keV scale. And so we do have some existing constraints that are sitting sort of, you know, very, very high up here. Okay, these are existing constraints. I don't know, maybe at like 10 to the minus 35. This is all units of centimeters squared for this cross section. Okay. And then there are a whole host of experiments or proposed experiments that sort of propose, you know, they sort of sit roughly over here. So there's a whole bunch of them, and these are sort of all the ones that have these EV-ish energy deposit thresholds. Okay, and so they typically are able to reach sort of towards that that MEV range. Actually, I see that I drew them very poorly. Let me let them go down a little bit better. Okay, so they do sort of probe down to that MEV scale. And then down here, what we have sort of complementary to these and really probing much deeper is different ideas that include, you know, using superconductors. And you can also think of using, as I said, Dirac materials, as well as heavy fermion systems. Okay. But what you see is that if we could construct large-scale superconducting experiments, these can really go way deeper, both deeper in cross-section as well as deeper in mass. And so just sort of projected reach, I think these numbers are still updated, let's say down to the 10 to the minus 42 over here, whereas these EV energy bounds would place us at, let's say, 10 to the minus 40 or something like that. Okay. So this is sort of the landscape of what current existing materials and proposals in the literature are capable of hope to be able to detect to improve our reach significantly into light dark matter parameter space. And the last thing that I wanted us to cover together is just the fact that you know, anytime somebody tells you about a new material that they have for a dark matter experiment, then those experiments, those materials can actually go a step further. Okay, so this is what I want to show you now, is that you can actually get 2 for the price of 1. Okay, so how does this work? So as I said, the idea is that any target material can actually go further. Okay. So if you think back to that energy guideline that we described together today, then we talked about, okay, if dark matter is scattering with my target, then the maximum energy deposit is the kinetic energy that it's carrying. And that meant that, you know, that there was a difference of 6 orders of magnitude between what is the size of my energy deposit compared to what mass of dark matter I can probe. Okay. But there's another process that could also be happening, right? I could have dark matter, instead of scattering with my material, an alternative is that dark matter maybe is coming in and is being completely absorbed by the material and not coming out. Okay, so instead of a scattering event, we can also think about absorption. Okay, so we also have to add on the possibility for absorption Absorption. How do we spell absorption? Absorption. Okay. So the idea is that here's my dark matter, which is going to come in and hits my target. And, you know, as we said before, instead of dark matter scattering out, maybe, you know, the target gets excited, something happens, it's going to emit. So it's going to emit electrons or photons or whatnot, but the dark matter isn't coming out. Okay. So in this case, what is the energy deposit into the system? It's no longer the kinetic energy that the particle is carrying. It is literally the entire mass energy of the particle. Okay, so there is, in this case, we have no outgoing dark matter. And so the deposited energy is the entire mass energy of the dark matter particle. And so
sorry,
that
Yonit, this is, maybe you said it for a boson.
Yes, of course. I can only have this happen for a boson, yes.
Okay.
Yeah. But nothing that we said until now was dependent on whether it was a boson. This indeed, you usually plot for you know, so the typical particles are going to be axion-like particles or dark photons. Yeah. Yeah, the lines here, I'm not being cautious. This isn't meant to say fermion at any point. It was just to designate different identities of particles. Okay. So, but what this means now is that if we think of that energy guideline that we drew before, okay, so here was my, right, we had deposited energy and we divided it. We had KeV and we had MEV and we had KeV and we had EV, of course, going through it as a magnitude down, and we talked about going down to MEV. And what we said was that, okay, if I wanted to look at the mass of dark matter, so I now just want to emphasize that this was dark matter through scattering. Okay, so through scattering, I was sensitive at KeV energy deposits to GeV particles, for EV energy deposit to MEV particles, and at millieV down to KeV. But if I have a system that's sensitive to KeV energies, then while it's true that for scattering, it's going to be sensitive to GeV masses, if I want to talk about absorption, so here down here is going to be dark matter masses via absorption, then if it's sensitive to KeV energy deposits, through absorption, it's now sensitive to KeV masses. And if it's sensitive to EV energy deposits, then it's sensitive through absorption to EV masses. And if it's sensitive to milli-EV energy deposits, then now I can also probe milli-EV masses. Okay, so this is what I mean, that we actually get two mass ranges for the price of one, because what we've constructed in our, you know, in our laboratory is something that's sensitive to particular energy deposits. And by considering the whole suite of types of events that could be happening, types of different topologies of the interactions of dark matter with our materials, then just being sensitive to these energy deposits enables us to probe, constrain, or detect dark matter masses in two mass ranges for the price of one. Okay, so that kind of concludes what I wanted to share and chat with you guys about today. So maybe I'll just sort of summarize. Look at the blue. Just sort of to summarize our time together. Hopefully, I've managed to convince you that dark matter is a very exciting field of research. So together, we've worked through a lot of interesting developments that are really happening right now, you know, really bubbling ideas that are happening now, different mechanisms to set the relic abundance of dark matter. We've seen how we could also perform model building in very generic ways. And we've also discussed interesting ways to detect dark matter. And I really hope that I've given you less the details of all of the particulars of these ideas, but really a way how to think about this in sort of a creative way. To really think outside of the standard box. I think that's really, really crucial, a really crucial understanding that it's great to think outside of the standard box. And my big hope is that you guys, as you amazing students, as the future, that you come up with the next incredible mechanism for dark matter, the next amazing model, the next incredible way to detect dark matter, that you're going to win the Nobel Prize, and we're going to find out what this mysterious stuff actually is. So I'm looking forward to your next big dark matter idea, because I really think that the best ideas are still ahead. And I'll thank you guys for your time.
Okay, thank you very much, Yonit, for these 5 lectures on dark matter and for this very optimistic conclusion and encouraging conclusion for all the students. I see a lot of people are clapping here on Zoom, so you cannot hear that.
Thanks.
If you want, you can unmute yourself so we can all. I cannot hear that. Okay, I do that. There is, of course, still time for the last question. I remind you that there is no discussion session today, so this is the last chance to ask questions to Yonit about today's lecture or even previous ones or anything you may have in mind.
I have a question, a quick one.
Sure.
What do you think about this gravitational detector proposal that was put out few years ago? You know, using this array of pendulum to see if dark matter passes through and excites this pendulum. I don't know what to think.
Yeah, I think it's cool. So I'll say in general. Okay, so also from the detection side, let me first say from the detection side, you see I've sort of stayed in the energy regime where I'm thinking of dark matter really as a particle rather than going to sort of the lighter side of the dark matter where it's more useful if I'm thinking of how I'm gonna detect it to think of dark matter as a field. And there's also a lot of really cool stuff. It's just, you know, it's hard to fit in material in just 5 lectures, but there's a lot of cool ideas for also how to be searching for dark matter when I think of it more as wave-like than particle-like. And yeah, I think, I mean, those, I think really it's very rare, you know, unless there's something like wrong with physics, which I don't think there is in that case. I think that all of these different ideas that people are putting forward are super exciting. And from my perspective, you know, we really have no idea where we're going to find dark matter, what's the right mass scale. And so I think that the more diverse our searches are, the better, you know, we're doing better science by sort of looking. We should be looking wherever we can. So if you have a great idea and even if it's really, really wacky, that's also one thing that I've really learned. It is totally fine for an idea to seem crazy at first, okay? It might be that your crazy idea is going to turn out, maybe you won't even realize it when you write your first crazy paper, you're going to realize it a year later or 2 years later. Maybe your crazy idea is completely generic in theory land, okay? Or maybe, you know, your crazy idea, which you think, oh, this could never happen, it's going to turn out that some experimentalist has like a little device sitting in their laboratory that you can already, you know, with something that they totally didn't even expect to be using for dark matter, you could already be setting world-leading limits. So it's totally fine for ideas to be to seem crazy. I'm not claiming that idea is crazy. I'm just saying, thinking outside the box, like really take it to the extreme, not to the extreme where you're breaking down the laws of physics, but just because somebody hasn't thought of it already doesn't mean that it's not a good idea. Just because somebody told you, somebody even who you think, oh, they're really smart, they know, you know, I think that you should always doubt, okay? When I was a student, I remember somebody, you know, my advisor or somebody in the department saying, you know, if dark matter is a thermal relic, then our experiments, like the xenon type experiments, are going to find it for sure. And that is completely not true. And it's completely not true for a variety of different reasons. But primarily, it's not true because at the time when people said thermal relics, that equaled WIMP. And that's just 100% not correct. Okay, we now understand that. 10 years ago, we didn't understand that. Are those the only experiments that could then be searching for it? Also, absolutely not. WIMPs don't have to be, even within the WIMP paradigm, they don't have to be above the GeV scale. Okay, I can take literally that 2-to-2 process and shove down the mass as much as I want. So all of these things, you know, what I'm trying to sort of say is that it's just really, really important to try to understand the basics and then go as creative as you can and think about, you know, I think there's a lot also to be done with interfaces with different fields of research, just because there's a lot of knowledge that sits, you know, elsewhere. And the more that communities speak with each other, I think the better each community is going to do in their science questions. So yeah, I think those ideas are great. Other ideas are great. It's hard to say which one is going to be the one that's gonna do best. So I say let's go for all of it. My personal take.
Thank you.
Sure. Leonardo, I see a question.
So thank you again for the great lecture series. I have a question on the sensitivity plot that you sketched right before this last page.
Yeah, sorry, wait, we lost my iPad. Hold on. Yeah, this one, not to be taken too much to the scale,
right.
but yeah.
Indeed. So I see that it goes down to about 10 to the minus 42. So that would imply that the neutrino floor does not appear on the plot. Is that correct?
Yeah, so these curves that I've just shown you are sort of the standard like apples to apples that people that are typically appear in the literature, and these are, so bounds of course are always not neglecting backgrounds. Those are, if I set a limit, I've understood how many events I see, and based on that I set where's my where's my 95% confidence level curve sitting. But typically for projections, what people do, unless you're already talking about a very concrete experiment where to compute what exactly is your background rate that you're expecting to happen, then you sort of, to compare apples to apples, what you're doing is assuming zero background. Okay, so this would correspond to, with Poisson statistics, like 3 events. Okay, so in a kilogram year, typically, this is probably, I think, the kilogram year curves that I've shown you over here. So in general, these curves are assuming no background. And of course, a great question is, okay, what are backgrounds? And one obvious one to come up is to talk about the neutrino background. I typically don't like to use the word floor, even though sometimes I accidentally say it, because floor assumes as if, oh, I can't go beneath it, which I don't think is necessarily true. But it's interesting because if you think about how the neutrino background is actually behaving, it behaves quite differently than what you're used to thinking. When we think about like the big WIMP, these huge experiments, then they're pushing down as they get bigger and bigger and bigger, and eventually they are going to hit that, right? And they're going to be hitting that, background. But when you go down to these lower masses, the neutrino behavior is actually quite different. So for instance, for superconductors, if I think of like a milli eV energy threshold, okay, let's say in this futuristic experiment that somebody is going to build, they're going to have a milli eV threshold, and these experiments typically go like 3 orders of magnitude in their dynamical range. So it's not like they go from milli eV up to infinity. There's usually around 3 orders of magnitude of like the acceptance of where they can see energies. And if I look at milli eV, then up to eV of energies, in a kilogram year of exposure, you actually get less than 1 event from a neutrino. Okay. Interestingly, if the threshold is actually higher, just because of if you compute what the neutrino rate is looking like, when you go higher, you might expect to actually see 3 events, and so you can fold that into your projected sensitivity. But just sort of to keep in mind, of course, you have to care about what are backgrounds. Can you understand backgrounds, and what are they? But in particular about neutrino floor, it's actually the neutrino background. It behaves a little differently than sort of the WIMP plot intuition might make you think.
Okay, thank you.
Sure. Are there any other questions? If not, I realize, can I show you guys the closest I've ever gotten to my crocodile challenge? Do you guys remember the crocodile challenge from lesson 1? Is that okay? Anybody who doesn't want to see the crocodile challenge is welcome to. But let me just show you. This is the closest I've gotten. I hope one of you gets way closer. And if you have a crocodile appearing in your paper, please let me know. Send me a note, okay? So here it is. So it was actually in the context of SIMPs. And as I mentioned, we've worked through a few different mediators. One of them is axions. So this is a plot that almost made it into the axion paper. I'll show it to you here. So here's my dark pions, okay? Dark pions. So here's my 5-point interaction, which we needed for SIMPs, right? So here's pions. And here's what almost happened. These pions were interacting with an axion-like particle, which I'll call A. And these axions were then going to electrons, okay? And just because we want it to really look like a crocodile, let's imagine we're also exchanging photons there, okay? Then this diagram would have been a fabulous crocodile. Here's an eyeball, and here's some legs I could attach to it. Unfortunately for me, this diagram, this vertex over here in the particular version of the gauge group, the number of flavors that we needed equaled 0. And so my crocodile had to be put aside, only to reappear in instances such as this. So anyway, if you get closer, please, pretty please let me know.
Okay, so I guess we also finished the lectures with the homework for everybody, but there is another question.
Yeah.
It's a quick question. It's about crocodiles.
Okay.
have you heard of the crocodile birds and their relationship with crocodiles? I mean, some experts said it's false because crocodiles don't need to clean their teeth and so on. So I'm just wondering what you think about that.
Wait, I missed crocodiles, and what was the relationship between crocodiles and
birds?
Oh, crocodile birds. I've never heard of crocodile birds. Can you send me a link? Now I'm excited. Send me a link and then I'll let you know what I think. Let's do it that way.
Ah, I see. I thought you must be an expert of crocodiles, so that's why
I somehow have never heard of crocodile birds, so this is
okay. There's a kind of misconception that the birds have a kind of symbiotic relationship with crocodiles.
Yes. Yeah, I don't actually know what to think of that. I mean, birds are remnants from the dinosaur ages. So are many bugs. So are crocodiles. One of the reasons I'm fascinated by crocodiles is because they're remnant from the days of the dinosaurs, and I think it's incredible. But I can't say more than the sentence I've just said now. So.
Okay.
Any other question? Okay, so I don't see any other question from the audience. So thank you very much, Yonit, again.
Thanks, everyone.